I will start talking about systems with weak noise and describe a general strategy that can be employed to compute the stationary measure, what is called in Friedmann-Wanzel theory, the quasi-potential, and we will see an application of these to a set of interacting diffusing particles that are weakly interacting. And then I will move to another set of problems that is what most interests me at the moment, what I've mostly worked on in the last years, that are active systems. And if the first part is going to be rather formal and theoretical, and if someone of you fall asleep, I hope to wake you up in this second part. So so my collaborators, the first part of the talk has been done in collaboration with Freddy Boucher and Christophe Gavetsky, both in Lyon. And the rest of the talk has been done mainly in collaboration with Mike Cates, part of it with Elsen, with a postdoc with Mike, Julien, Frederic, and Etienne, that is another postdoc of Mike. So let me start from the first part of the talk, where we will discuss systems that are in weak noise. So we will generically consider a system where described by a variable x that is stochastic and is subjected to a noise that is in some sense weak. We will always denote by Q the covariance of the noise. And in Friedmann-Wanzel theory, a central object is what is called the quasi-potential. That is nothing else, essentially, that the rate function of the stationary measure in the weak noise limit. So it is so systems with weak noise have some attention in statistical mechanics community in the last years. The main reason is the fact that Iona Lasinio, Bernard Derrida, and collaborators did realize that a large class of systems, such as stochastic lattice gases that are weakly driven out of equilibrium, can be described. So an example is WASP, where the hopping rates on the left and on the right differ only of a quantity that is order 1 over the number of degrees of freedom. This kind of system can be described macroscopically. So if you describe the evolution of the density field through a weak noise stochastic, a weak noise partial differential equation where sigma is the mobility, d is the diffusivity of the system, and the noise is weak in 1 over the number of degrees of freedom. And in this context, the quasi-potential is nothing else than the non-equilibrium free energy of our system. So computing with the quasi-potential is typically a difficult problem. In particular, it's rather well known since the 80s, since the work of Friedlin, that the quasi-potential can essentially be, well, actually in physics is known since much before. The quasi-potential can be computed from a variational problem that comes from essentially a WKB approximation of a path integral. So the idea is that this is the action, and so is the weight of a given trajectory x of t, and the quasi-potential is just given by the minimization over all possible trajectories that starts from the attractor and end up in the point in which you want to compute the fluctuation of the Friedmann-Wanzel action. Now, if you know the quasi-potential, so now it's known that the minimization taken on a single trajectory. So what this means? It means if the system wants to create a fluctuation, it wants to fluctuate from x naught to a given point x. There are, different realization, of course, will follow different trajectories, but in the weak noise limit, they will all concentrate around one trajectory, that is the pink one, that is written there. And this trajectory is actually given by the solution of what is called the Instanton dynamics. So it's just the solution of these dynamics with appropriate boundary conditions. And this dynamics, you see, depends itself on the quasi-potential. So what does this mean? It means that we have a circular structure somehow. So if you know the quasi-potential, then you know the instanton dynamics. If you know the instanton dynamics, you can solve it with the boundary condition that you start from the attractor, you end up somewhere. And if you have this solution, you can plug it into the action, and this gives you the quasi-potential itself. So it's a circular structure, and which will be very important in the following, and only in the case in which we have an equilibrium system, then the way in which the system creates a fluctuation is the same as the way in which it relaxes back to the attractor. And in particular, this means that K is actually equal to the drift of the instanton. Okay, so the main thing that we have been trying to do is the following thing. Suppose I have a system that, so computing quasi-potentials for a generic non-equilibrium system is typically very, very difficult. Analytically, it's typically impossible. So suppose you have the following problem. Suppose you have a dynamics that depends on an external parameter lambda, and suppose that can affect the drift or the diffusion matrix. And suppose that you are able to, you know the quasi-potential for a given value of this parameter lambda, say lambda equal to 0. Then the question is, can we calculate, thanks to this circular structure, can we actually calculate the quasi-potential perturbatively in these parameters? So in literature, there were some studies around this. However, they were mostly, actually all of them, first-order theories, so calculation of the quasi-potential at first order in lambda, and they were mostly concentrated on finite dimensional systems. So what we have proven, and I will actually not go through the proof of this, but we can discuss it privately if someone is interested, that such an expansion exists and is actually constructed. So this circle can actually be broken perturbatively. You can expand the quasi-potential just in a Taylor series in lambda, and you can find explicit construction of these of each order. And the interesting thing of the story, so a difficult part of the story has been to describe the to prove the existence of such an expansion and the well-posedness of these expressions, as well to prove that actually these series convergent unless in the regular case in which both the drift and the covariance matrix are analytic. So in this case, you have finite radius of convergence. But there is also another thing that is rather interesting to me, that is that in order to break this circle perturbatively, you don't need to calculate always the instanton dynamics. So the point is that you only need the instanton dynamics, the solution of the instanton dynamics of the unperturbed problem in order to calculate the quasi-potential at all orders. So these are explicit formula. I do not write them explicitly because beyond the first order they are a little bit complex. But there are explicit expressions of Sn. So the idea is that if you are able to compute the solution of the instanton dynamics of the unperturbed problem, then you just solve it, then you squeeze it in some functional that depends on the quasi-potential at lower order, and you get the quasi-potential at the next order. So as an application of this problem, of this theory, we consider a problem of diffusing particles. One of the simplest problems of non-equilibrium, continuous non-equilibrium systems that are diffusing particles that are interacting with a mean field scale. So this is the model we considered, that essentially a simplification of the Kuramoto model So you have n particles on a circle that are denoted by an angle theta. Then they interact to a potential that is mean field, and that's very important. I will tell you afterwards why it's very important. So the fact that it's mean field is encoded in the fact that you have this Katz scaling. The interaction is weak, it's order 1/n. And the system is driven out of equilibrium by the presence of a field F that is constant. It's a non-gradient function on a circle. And there is also an external magnetic field H. So already the typical behavior of this system is highly non-trivial. So that's the phase diagram that we were able to compute essentially in a completely analytic way. In particular, we were able to find all stationary states. There are several. And to analyze their stability, there is a complex bifurcation diagram. In particular, this is a Hopf bifurcation, this is a saddle knot bifurcation, and here there is complex objects. I will not go through this. All in all, anyway, for high temperature or high magnetic fields, the system is stationary in average, while inside this region is actually periodic. So what we did was to compute perturbatively the quasi-potential in the region in which the system is typically stationary. So how do we do that? So the first step is to describe it from macroscopic point of view. So what do I mean? You can go, you can introduce the empirical measure of the system, and it's well known in literature from the work of Dean in 1995 that this empirical measure solves formally an equation that is called Dean equation. That's this object here. That seems complicated, but it's actually not. So if you forget about the noise, this guy is just the Fokker-Planck for a single particle that moves in the mean field potential. The mean field potential is U convoluted with phi n. So writing this equation allows to retrieve results that are rigorously known, meaning that if you take n to infinity, then you kill the noise. If you look at smooth solutions of this equation, then you get back the mean field approximation of the dynamics. You say that the empirical measure follows the mean field approximation of the dynamics, which is something known rigorously in mathematics. And beyond that, if you take n large but finite, still you are able to go through Friedlein-Wansel theory, so to write the probability of a realization of phi, of a trajectory of phi, and this is again in agreement with rigorous results from large division from mathematics. Now, the fact that the noise is weak, and this is very important, is due to the fact that I'm dealing with a system with mean field scaling. So it's due to the fact that the coupling is weak. That's the reason for which the mean field scaling is important. Okay, so we performed perturbative calculations of the quasi-potential of this model in a number of cases. What I will present you is the case where you compute it close to the case in which the dynamics are of free particles. So around J equal to 0. If J is equal to 0, you know the quasi-potential because you have just a set of non-interacting particles, and this is given by Sanoff theorem. That's written here, where phi naught is the stationary solution of your system, is your typical state. And perturbatively in J, you can indeed calculate the quasi-potential, did explicitly at first order. You can show that the quasi-potential takes the form of an homogeneous polynomial. At first order, it is a degree 2 polynomial in phi with a kernel F1 that is depicted here. We have not really compared these predictions to particle-based simulations so far, but the fact that the perturbative theory greatly improves the approximation of the unperturbed theory can be already seen by looking at the typical state, because the typical state can be computed exactly, so that's the red line. The typical state of the unperturbed problem is the green line that I'm not sure you can C, but it's kind of here. And the blue is the typical state of the perturbation. Now, the perturbation, this approach could be generalized at any order. There is no computational difficulty that you buy by doing so, but we were a bit lazy. And correspondingly, of course, you can compute fluctuations of observables. An example is the magnetization, that is the typical order of parameter of these problems, magnetization along the x or the y-axis, and here are depicted the rate functions that we obtained. Okay, so I will not go in greater details on this problem. I will instead move to the second and the third part of the talk, where I will be mostly talking about active matter, and we will see other two problems that are somehow close to equilibrium in different sense. So first of all, what are active systems? So active systems generically are objects that are able to transform some fuel that is present into motion. And examples are from natural world, bacteria, algae, or we are nowadays able to make them, to make synthetic realization of active matter, for example, through autophoretic colloids or microrobots or shaken granular matter. And one of the reasons for which active systems are actually, have actually captured the attention of many physicists is the fact that they show very intriguing collective behaviors that are impossible at equilibrium. So one of them that I will talk a little bit about later on in the third part of the talk is what we call phase separation. So phase separation is a phenomenon first put forward by Julien Tailleur and Mike Cates about 10 years ago. The idea is that if you have a set of particles that are purely repulsive but active, still they do not stay homogeneous, but they tend to phase separate in a dense and gas-like phase. Now, one of the minimal models that we employed to analyze this kind of collective behavior are what we call active Orsa-Uhlenbeck particles that are just a set of n bodies, each of them that moves with a velocity that is persistent in time. So a velocity that has some typical decorrelation time scale that I will call tau. And of course, besides their natural motion, sorry, this should be u. Sorry. So that's the self-propulsion velocity, this guy. So we will take, active Orsa-Uhlenbeck particles have self-propulsion velocity that is a Gaussian random variable, but correlated in time. And they interact with a two-body potential that I will call u. So now this problem is a problem that has a well-defined limit to equilibrium, because if you take the limit of tau to 0, then you end up with an equilibrium system. You just become unit random variables, unit and delta correlated, become delta correlated random variables. So you know the steady state of this system is just the Boltzmann-Gibbs measure. While for tau different from 0, we were able to compute the stationary measure perturbatively in tau. Actually, does not completely fit in a large deviation framework, because we actually did it for any temperature. So we also looked at corrections that arise, that are order tau to the 0 in the stationary measure, and that's the stationary measure we obtained, which is rather surprising from some point of view, because this perturbative calculation has shown that you can have, that we do have a non-Boltzmann-Gibbs stationary, that's the blue stuff, at order tau, but at this level, we have time reversibility. So if you compute the entropy reduction, that's 0. And this fact allows to put forward effective fluctuation-dissipation theorems for this system. In particular, if you perturb the dynamics to constant force, you realize that at order tau, the fluctuation-dissipation theorem that you normally have in equilibrium is modified by a new piece, which is actually well captured in numerical simulations. Sorry? Well, it does effectively because it enters in the dynamics of the eye, but I mean, well, I mean, the stationary measure does, but the fluctuation-dissipation theorem does not, as in equilibrium. Which is somehow what is, I mean, you always have a linear response formula, right? For any non-equilibrium system, the fact that it does not depend on the gradient of the potential explicitly is what is due to the fact that you have an effective equilibrium. Which if you have. Yes, but I mean, we are perturbatively in tau, or if you wish, we are perturbatively in these guys, so yeah. You cannot stretch maths too much. Yes, it's proportional to the persistence time. Yes. No, because I've rescaled velocities. So that are the actual velocities with which particles move. So if tau is really 0, then you get back to the normal fluctuation-dissipation theorem and you drop this term. But if tau is not 0, is small, then you have a correction. P is the square root of tau r dot. It's well defined because, yes. Okay, so I will go to the third part of the talk, in which we will encounter a set of systems that are somehow not too far from equilibrium in a very different sense. And I will discuss a phenomena that we call incomplete phase separation in active matter, which is something we have worked on with Mike and Elson rather intensively in the last times. And we are, I mean, the corresponding publication is now in preparation. So let me show you again this slide. So what is phase separation in active matter? And let me explain it a little bit better. So this is typically what you see when you simulate a system here. These are hardcore particles at sufficiently high persistence time such that, I mean, to drive this instability to a phase-separated state. Now, why this happens? So this happens because time reversal symmetry is broken in the system. So in which sense time reversal symmetry is broken in this system? So there is a trivial sense that is not what I mean. That is because fuel is transformed into motion. But fuel is not in my models, so that cannot be the cause. So how time reversal symmetry is broken? It's essentially due to interactions. So assume you have two particles that tend to collide head-on, I mean head-to-head, head-to-head. Then, in order to resolve this collision, you have to wait quite a long time in order for the direction of the self-propulsion to diffuse and so that they can go away. But in a time-reversed world, they are not colliding head-to-head. And so what happens is that only a short pause is necessary for them to slide past. So this is essentially the reason for which phase separation happens, meaning that if you have repulsive particles, they are going to accumulate and slow down typically when they interact. So formally, this idea has been first put forward by Julien and Mike 10 years ago, and the main idea to describe this system is to observe the following thing. It's too difficult to start from scratch from a system that is really composed of two body interacting particles. So let's first do a phenomenological step where we assume that particles actually have, that interaction actually results in a self-propulsion velocity that depends on the density. And let's assume that the self-propulsion velocity goes down when the density goes up. So let's take this as our starting model. And then it's rather simple to show that if you take the persistence time limit to be small, then, and you do some coarse graining that is essentially the same thing as I was presenting before, the Dean equation, then what you end up, surprisingly, is that you have an effective equilibrium system when you describe the evolution of the density field. So this is the free energy that you obtain with this approximation, and it's a double well potential. And you know that a system with conserved order parameter in equilibrium with double well potential undergoes a liquid-gas phase separation, which is what we interpret as the phase separation in active mode. Now, this theory is beautiful, it's extremely simple. The problem is that in many situations, it actually, well, or at least, there are many situations in which it does not seem to work. So, or at least that there are many situations in which something more complex seems to happen. So in particular, this is what we typically see in experiments. This is an experiment by Palacci and others in 2013. These are photoactivated colloids. And you can see that they tend indeed to form clusters, to aggregate. But these clusters are highly dynamical, and importantly, they do not coarsen to the system size scale. On the other hand, in simulations, something a little more complex than just phase separation happens. So these are simulations performed by Joachim Stenhammar in 2014. There are about 40 million particles. The bright spots are the dense regions, and they are coarsening. So ultimately, this system is going to a unique blob of the yellow region. But you see that in this yellow region, there is a kind of continuous formation of bubbles that are then ejected outside. Okay. So these two things are what we call incomplete phase separation. And in order to describe them, we have built active field theories which essentially can be, which are summarized here. So this model seems very complex, but it's not. It's not because if I forget about the zeta and the lambda term, so the red and the blue terms, this guy is just the model B of equilibrium liquid-gas phase separation. And it's natural to start from, so what we are doing is just to minimally modify the model that we have in equilibrium for liquid-gas phase separation, model B, or conserved by Ford theory, with the terms that are lowest order ingredient and do not derive from a free energy, so do break time reversal symmetry. So there are two such terms. The lambda one, I will not talk about this because it only quantitatively modifies the physics. I will mostly talk about the zeta term, which is a term in which you see the current is not curl-free. So what does this mean? It means that if I have a system where I have a density modulation, so I assume I have a system on a ring, I assume here it's denser, there is a gradient of density, then what happens is that the zeta term is pumping a current on it. Okay, so this model is not purely phenomenological. We can derive it from explicit coarse graining of particle systems. And the main idea to do so is to realize that the complex effect of two-body interactions cannot really only result in a density-dependent field. But this is clearly some kind of mean field approximation. And in a similar spirit to liquid state theory, in which you divide the potential in we divide the potential in an hardcore part that we, in an hardcore repulsive part that we encode in the density-dependent speed, and while we retain the tails of the interaction potential of the two-body interactions potential in E. So it's possible to do explicit coarse graining and gradient expansion of this guy, which ends up in the active field theories I was talking about before. And the interesting thing is that there is the sign of this non-equilibrium parameter zeta is only found in terms of a very simple property, that is that the tails of the interaction potential are either attractive or repulsive. This will be important in the fall. So that's the phase diagram that we find. So for zeta, so that's the average density of the system. That's the non-equilibrium zeta, the non-equilibrium parameter. And so for zeta 0, it's model B, it's equilibrium liquid-gas phase separation. So at low density, we are dilute, it's a gas. At high density, we are dense and homogeneous, it's a liquid. In between the red lines that are the binodals, we are actually phase separated. Now, if we switch on a little bit of activity, what happens is that at the beginning, nothing essentially. So it's okay. Of course, we quantitatively change, for example, the values of the coexistent phase, the density of the coexistent phases, but beside that, nothing more. But if we cross a given value of the non-equilibrium parameter, then everything changes. And in particular, we either completely destroy phase separation, going to this kind of bubbly phase where these clusters do not grow, to the full system size scale, or we have a phase separation between this bubbly phase and the dilute phase. Sorry? That's numerics. That's okay, we can discuss this later on, but very generic. So okay, so we start from, the explicit coarse graining is done from here. So you assume, so what is this? Again, I can interpret this in two ways. Either I say, well, I have quorum sensing particles. Okay, they will not interact only through quorum sensing. There will be other effects, such as excluded volume. Sorry? If I have only quorum sensing, I don't. Yeah, so I need this U. So I need some kind of tails of the interaction, or, something that is not encoded in a density dependency. Not even a self-propulsion speed that is dependent on the gradients of the densities. But we can discuss this later on. Well, it means that the bubble seems to be continuously deformed too. No. Well, these do not grow to a system size. These do. Bubble and dense. Well, okay, this is the mean field binodal of this. So here you do not nucleate bubble anymore. Well, it's the same thing as, okay, in equilibrium, do you have a phase transition? It's the same thing. Well, but they have well-defined density. So I have a density of bubbles that is well-defined. Yes. Yes, it is, yes. But I will, okay, so I will give you a little bit more details in a moment. So if I have repulsive interactions, if I have kind of hardcore interactions plus a repulsive tail, okay, then I expect to have the zeta term positive, which is the phase this is the phase diagram for zeta positive. Yes, because I expect pairwise forces, a correct treatment of, a reasonable treatment of pairwise forces is to use this kind of liquid state theory approach in which I divide the interaction in a hardcore part plus the tails of the interactions. Now, the hardcore part will result in a density-dependent speed, or at least I treat it as this. And the tails of the interactions, no. And by doing coarse graining of this guy, I end up in these active field theories with the zeta term. And if the tails of the interactions are repulsive, I have zeta. So the dynamics of this bubble is interesting and shows breakdown of time reversal symmetry. So in this phase that I was talking about before, in this bubbly phase separation, what happens is that from time to time in the liquids, I do nucleate a gas bubble, and then this gas bubble grows, but also wiggles around, diffuses, until when it, well, actually, diffuses is probably not correct, because we can talk privately about this, but then at some point, it meets the interface and is ejected out. The opposite mechanism, the opposite direction never happens, I mean, or at least it's not typically observed, which is, if you want, a nice example, I believe, of time reversal symmetry breaking, or the fact that fluctuations in equilibrium systems as these are created differently from how they are, from how they relax. Now, if I take zeta negative, it's easy to realize that the system is symmetric under zeta phi minus zeta minus phi. So what this means is only that the phase diagram for zeta negative is the same as before, except that it's flipped. So I've been lazy again, so I've not changed the color. Now bright is yellow. I mean, now bright is dilute, dark is dense. But what this is saying is that at low densities, I expect to have this kind of cluster fate. And as I was saying to Rob before, so we have at the moment, I mean, some indication that the density of bubbles is a well-defined quantity in this large system size limit. So how can this happen? Because there is so how in particular, so because in equilibrium, there is a phenomena that is very generic, which is called Ostwald Ripening. And it's the reason for which when you put water in your anise-based drink, like the pastis, it becomes fake. There is this phenomena that essentially tells you that if I have two droplets of different size, then the pressure inside one, I mean, the biggest droplet is smaller than the pressure inside the smaller droplet. So what happens if you let them relax is that the small droplet shrinks in favor of the bigger one. And this is very well known since long time, essentially from the 50s, 40s, from Lipschitz. It's a mean field argument, so there is no noise. It's extremely generic. You find it in systems with without hydrodynamics. I mean, in Model B, in modifications where you put hydrodynamics. I mean, it's extremely generic, and essentially tells you that just assuming quasi-static diffusion of the droplets, you can derive an evolution equation for the radius of the droplets, which tells you that when you take a drop that is smaller than a given critical value, that depends essentially on the value of the density field at infinity, then it shrinks. And when you nucleate one that is above this critical value, it grows. Now, this also tells you that there is a scaling law, in particular that the radius grows as t1/3 at large times. And what happens to this mechanism when you introduce the zeta term? So what happens is that it is extremely strongly slowed down. It's strongly slowed down. So you can follow essentially the same argument that leads to Ostwald Ripening. And what you discover is that the interfacial tension, sigma, sorry, I forgot to put it here. So sigma is just the interface, the surface tension, is exponentially depressed in zeta. Okay, so we can go through that, but in this, I mean, for me, surface tension is just the integral across of the interface of the derivative of the field. That's all. So that's something I call surface tension. We can call it differently, but it's something mathematically well defined. Now, what you discover is that still in a mean world, the droplets should, I mean, droplets that are greater than the critical value should grow. But what you also discover is that the time scale for coarsening or for shrinking becomes exponentially small in zeta, and the small, I mean, that the critical radius becomes instead exponentially small in zeta. So we don't have analytical theory to explain these phase transitions so far, but we have kind of physical understanding. When you have zeta different from 0, the tiny fraction of noise is enough to make the time scale for nucleation comparable to the time scale for coarsening. And when this happens, you are very far away from a mean field system. And if you just assume that, so if you assume that you have a large deviation scaling of the nucleation time scale, so that is exponentially small in 1 over the noise, then you derive that this critical value of zeta increases when the noise goes down, which seems to be, okay, these are kind of preliminary results, but seems to be reasonably found in simulations. So I will stop here. Thank you very much for your attention, and these are the publications I've talked about. Thank you.
Sorry. Can you say something more about the exponential suppression of the surface tension? Is that really, because it appears, the exponential factor appears next to sigma, but doesn't necessarily mean that.
Yeah, okay, maybe it's okay, yes. So let me see if I have a slide. Yes, okay, so maybe we can discuss, I mean, it's a slightly technical issue, so maybe we can discuss this privately. We don't, okay, so I don't have a physical argument to say that this should happen. I can go through exactly the same calculation as in equilibrium, and this is what you find. Now, I don't think that the surface tension actually can be interpreted as surface tension physically. Okay, so, but what happens? Okay, I mean, in order to derive this mechanism, you have to essentially go to define some pressure-like object, but again, I mean, okay, Yarif has worked a lot on this. I mean, it's very delicate to say whether pressure is pressure or it's not pressure. So here we don't really care somehow, in the sense that, you know, it's just mathematical objects that you can use in equilibrium have a meaning. Here, probably not really, but you can use them in the same.
For the overdamped Einstein-Uhlenbeck process, so there in the tau going to 0 limit, it looks like p should be a irrelevant variable, right? You should just get.
It should, sorry?
P, I mean, it looks like you just get a overdamped Brownian particle. So isn't it like p should be kind of irrelevant in the tau going to 0 limit?
So for tau to 0.
So that's just a overdamped Brownian.
Yeah, no, sorry, yes,
so
it's right.
Is kind of irrelevant, right? Why
sorry, yes, it's right. No, you're right. Yes, you're right. Tau to 0, you can trace out p. Yes.
So
you just have exponential minus u.
So p just goes to 0.
Yes, sorry.
But why is it useful to introduce p and
well, because for any tau non-zero, it's not what, I mean, you cannot only describe the system in terms of position of particles. I could have written these objects in terms, I mean, this stationary measure in terms of R and D, yeah, I mean,
But is there an advantage to doing this? I mean,
no. Sorry. I mean, yes, I should have presented this. No, it's completely clear.
So this one, do you get clustering now? If you put for finite tau, you get clustering. Good for this.
Finite tau?
Do you get clustering for?
Yeah. I mean, in this model, for finite tau, you get indeed phase separation.
But then
It's not in a perturbative regime. I mean, it's not in tau very small.
But then also there should be a time scale at which this cluster breaks up, right? Which is again proportional to tau or something, no?
Okay, no. So you're asking a different question. Sorry, I didn't get. So in this model for finite tau, we get. So what we were able to show is that we get complete phase separation if the interactions are purely repulsive.
But then,
we have not tried to see whether there is, I mean, within these active or Ulengbach particles, whether we have this kind of incomplete phase separation.
no, like for example, I mean, like even this active Ulengbach process, I can look at the process at a time scale which is much larger than tau, and then it looks like a delta fold process, right?
Yeah.
So even if you have this clustering, at some time still this clustering should again disappear.
I mean, the point is that the typical, I mean, in this scenario, when you are talking about a situation like this, tau is not small in any sense. So you cannot really think to this as something that happens close to equilibrium in tau.
But whatever the tau, I cannot just look at a much larger time scale and then doesn't it look like a...
I mean, for tau small, you have just, you know, you have, I mean, the stationary measure of your system is just epsilon, I mean, tau modified from the equilibrium one, which is exponential minus u, and, you know, for repulsive potentials, exponential minus u just gives you an homogeneous. Okay, but this is a much. If one wants to address this problem, I mean, using a much simpler system is a good idea because, you know, in this Kuramoto kind of system, we don't even know analytically the periodicity. So, it's extremely difficult. So the kind of expansion we are doing are, that we have done in this are away from the bifurcation. But there are cases where this could be done because, for example, if you take Orsan-Uhlenbeck particles, I mean just an Orsan-Uhlenbeck process, and this dynamics is solvable. Is very easily solvable. Now, if you perturb it whatsoever non-gradient object, you can compute the quasi-potential element. So this could be, I mean, if there is a model in this class that has that has a singularity in the quasi-potential, then you could look at what happens into the perturbation theory. So I would start from there, not from an n-body.
Okay, there are no more questions. Let's thank Cesare again.